So hi folks, and from this video onwards, what I'll be trying to do throughout this semester and maybe even in my next semester is that I'll be trying to revise my basics of analog, which starts all the way from passive circuits all the way to higher level, let us say two-stage op amps, BGR, LDO, all that. So I'll try to revise all of these things in a logical hierarchical flow, and thus I'll be trying to break all of my analog knowledge in chunks and notes, and I'll be trying to basically in a way try to revise them, and as an incentive for me will also record them. So I don't know if this will be helpful to anyone who wants to learn it for the first time or anything. I don't know, but it is just kind of a revision log for me. So I'm doing this. The reason why I'm doing this is because in my second year I'm doing a project which is on optics. It's about superconductor generation, so it's quite different from analog VLSI, and thus I'm trying to do this activity so that basically I'm also able to actively revise my analog basics. So, without any further ado and without any further context, because I think I have given enough, I'll proceed with the agenda of this video. So, from for this and couple next videos, what I'll be trying to revise is passive circuits. And to be more precise, I studied these passive circuit theory majorly from Shemia and Teaser, and I'll attach its playlist a link in the description. And I also refer to some other sources and my prerequisite knowledge, because although these passive circuits seem to be too basic and too easy, but if you mess up in these, then there is then all your interview and all your projects are forfeit, because this is the main thing that all the analog companies want from you, because these are the core, these are the soul of analog. Because even when you are building higher level systems, be it op amps, BGRs, LDOs, anything, PLLs, they all rely on the core intuition of how your RLC circuits are. So if you are able to break a big problem into simpler RC chunks and mostly into first order RC or RL chunks, then and you are able to analyze and understand them intuitively, then you can be a great analog design engineer. That being said, let us start the revisions. For this video, I'll try to focus my revision onto first order circuits. So let's begin. So first of all, let's go to the sources. So we know these standard things that sources are either independent or or dependent, right? So this is quite something simple, and some of a property that I think we all know about ideal independent voltage sources, that it can source or sink infinite current, which means that if I try to plot the IV characteristics of a voltage source, then it will be a horizontal line, and this vertical line, and this vertical line implies that it can source or sink infinite current. Yeah. Now, similar argument will go for the current source also. Now, I want to discuss one peculiar thing, and the peculiar thing is, if we all remember the definition of linear system, right? We all have studied signal system, and we remember the definition of linear system, and we know that we can define a linear system only when it satisfies two things. What are those two things? Homogeneity, homogeneity, and superposition, right? Homogeneity and superposition. So, some homogeneity superposition. So, the question is that is y equals to mx plus c a linear system by this definition where c is not equal to 0? It is not a linear system. Why? Because of this term, right? Because you can understand that because of this additional c term, this system will break. What will it break? It will break the idea of superposition, right? So from this idea, what we understood was that a linear system's characteristic must pass through the origin, right? Okay, this is very curious now. Why it is very curious? Because I just mentioned that an ideal voltage source and an ideal current source, both of their graphs Like for voltage, the IV characteristic will be like this, and for current, the IV characteristic will be like this. And when these guys are non-zero, that is voltage source non-zero, and current is source also is non-zero, then their graph will not pass to the origin. Now that begs the question that is ideal voltage source and ideal current source a linear system? As it happens to be, in our usual circuit analysis, we very easily say that these things are linear and we begin with the analysis, but in the very strict mathematical sense, these are actually not linear, but they are affine, right? So affine systems are basically a superset in which linear systems come, and for affine systems, the general expression will be y equals to mx plus c. And for linear, c is equals to 0. Yeah. Now, so just so that I can actually convince you why voltage source or current source is not truly a linear system is that if I express a voltage, ideal voltage source as a function of current, it is equals to a constant, right? It is equal to, let us say, Vs. Now, if I try to scale the current passing through this guy, so if I scale this current by A times, still the output will be Vs only, right? The output will not grow by A times. That's the idea because our ideal voltage source, as we said, already discussed, will maintain a constant voltage across it, regardless of the current it is sourcing or sinking. So from this alone, we can understand that it is not following the principle of homogeneity, so therefore it cannot be a linear system in that sense, right? But we use it quite comfortably as a linear system, as a linear device in our circuit analysis, but I still just wanted to discuss this small catch for people who are like too much into maths or want to be mathematically correct. So that's why I just mentioned this, but I did not mention this to like confuse folks. Definitely in our circuit analysis, we use it rampantly as a linear system. We apply superposition with the voltage sources, and it is very easily done with an ideal voltage source or current sources. But the idea was that these are not homogeneous, right? They don't follow homogeneity, and thus, strictly mathematically speaking, they are affine, not linear. But we can ignore this discussion, small discussion. But I just wanted to like keep it out there because I have written it here, so people might get confused, and that's why I'm just putting it down there, right? Then by the way, this outline that I'm following is of Shambhia Teaser's playlist only. So that's just like a quite short mind map for me, rather. So we know what finite energy sources are, right? Then we know about finite power source also, so it's not a big deal. And the definition of an amplifier, that is that output power must be more than the input power. And here we are talking about the signals of interest. We all know that by energy conservation, this formula actually should look something like P out is equals to P in plus P quiescent, right? Or PDC, right? So this relation must be satisfied, right? So this is inherently understood that this relation is followed. Here we are only talking about signals of interest, right? Like what is my output signal that I want and what was my input signal that I fed in. So this definition alone easily breaks the idea that transformer is an amplifier because we know that a transformer it will give n times or 1 by n times the voltage, but it will give the opposite the current but in opposite magnitude, so the effective power won't increase in the output, right? So that is the basic idea. Here I just expressed a transformer by a simple circuit model, and I've written its input apparent impedance where the transistor is n is to 1. It's quite easy to derive, so we won't go into that. Here now I have written delta to star transformation formula, and I think it is quite in order if we just quickly discuss it. So here I have just written that the in the if this the formula for delta to star conversion. So here we can see that RC is the impedance opposite to R3, right? So here we can see that in the formula that R3 is omitted in the numerator, and in the denominator we have all the resistances in summation, and this equation also makes dimensionally sense. And this is the formula for star to delta conversion, and here the numerator is constant for all the resistance value, and this guy only changes, which is basically the resistance opposite to RC, right? So quite easy to memorize. Again, the derivation can be done, but again, we won't go through it. Let us go to the main topic of interest, which is capacitive circuit. And in all our first order analysis, which basically deal with capacitors, the main idea is energy conservation and charge sharing, right? Energy conservation basically means that you can't basically destroy or create energy out of nowhere, and charge sharing basically means that in the overall system, the charge will be conserved. So basically, you'll be writing equations like C1 V1 is equal to C2 V2, where C1 V1 is the initial condition, C2 V2 is the final condition after you have made some changes in the circuit. But for time being, let us discuss this tiny example. Here, what I have done is I have basically fed a step input which goes from 0 to 2 volt to the series capacitor network, where we have also given an initial condition of 1 volt across the 2C capacitor, right? And so, what is the idea here? What we want to find is the steady state voltage across these two ways, right? Again, it's very important to define what steady state is. It's very much important that I talk about what steady state over here is. We all know this, that we usually talk about steady state values at infinite time, but it's important to mention that steady state also means that when the circuit is not undergoing any dynamics, that is, that that the current is steady, or current might be zero, or the voltages are steady, right? Now, here why I'm trying to emphasize on this, I think I'll elaborate on this later. But just we should keep in our mind that currents are stable, right? Like for example, one might argue that if I have a sinusoidal like this, and initially it was haphazard, so this was the transient and this is the steady state value. But this it was meant to be this, right? And initially it was this, so it is the transient, and this is the steady state. So here one might argue that the current is changing and the voltage is changing. So how is it steady state? But steady state is quite a loose term in that sense that steady state basically means that what is the desired behavior of that system under a forced input, right? So I think we'll go into discussing this later. But okay, let us just first deal with this example since it's ahead of us. So there are basically two ways to deal with this problem. One way is that you just apply superposition, and what you can do is you can just break the circuit into two chunks. One is that you just first assume that the circuit has no initial condition, and then as per this input, you find the voltage across these two capacitors. Then you remove this input, and then assume that only the initial condition was present, and then see that how this initial condition charge will redistribute, and then you add the two and you'll get your output, right? So that is what we can easily do if we were to solve this right now. What we will do is that we'll assume that this initial condition with voltage is not here. Then what will happen is that we can see that this is the larger capacitor, which implies that it will have a smaller drop across it, right? And so what will happen is that if I write VC, and I tried to write 2 VC. So the intuition behind the larger capacitor will allow smaller voltage drop across it is because Q is equals to C times V, right? So when I'm applying, see, in series, the capacitors have the same charge, right? So here, since this is C value is more and Q value is same, so V will be Q by C, and since C is more, voltage change will be less. Alternatively, since capacitor is large, it has capacity to hold more charge, so therefore the voltage increment will be lesser. Because if the voltage will just shoot up, a time will come when that capacitor will break down because of that huge voltage built up, right? So that is something that we can again intuitively understand, that a bigger capacitor will allow lesser voltage change across it, which implies that it will be inherently able to store more charge. Let us get to this discussion. We are getting way too deviated, I believe. So what will we see here when we are ignoring the initial conditions? So here, again, as I said, since it's a smaller cap, so it will have what more charge. So it will be 2 by 3 times this again into 2. And what will be V2C? V2C, again, as I said, it will hold the lesser amount, it will hold the lesser amount of voltage. Then it will be 1 by 3 times 2. Yeah. Now this is without initial conditions. Now we will consider the initial condition and remove this source. So the circuit will then look like C, 2C, and here will be 1 volt, right? And here now we can apply the charge conservation, right? So here we can just say that 2C times 1, or rather I can say that these two will come in parallel. So I can just say that 3C times 1 is equals to what? Sorry, I wrote the wrong expression. It will be 2C is equals to is times 1, by the way. 3C times Vx, and so Vx will be what? 2 by 3. Now the question is that what will be the polarity of this guy? What will be the polarity of this guy? See, initially if you notice that this guy folded from here to here, so since we are defining VC polarity as plus minus, so here this VC charge that we will obtain from here will be minus 2 by 3, right? I hope it is quite easy to understand because this is the positive terminal with respect to how we have defined the voltage. So it will be minus 2 by 3 and this guy will be 2 by 3. So now that we have established that VC will be minus 2 by 3 when we are taking the initial condition and V2C will be 2 by 3. So when we add these guys together, we'll get our answer. So here we will get V2C is 4 by 3 and this guy will be 2 by 3, which is the expected answer. Right? So this is one way to solve that we can easily apply superposition. I am just trying to demonstrate the thinking. That's why it took me a bit more time, but we can actually do this quite quickly by thinking it in our head also, right? Another way, and this is a way that I personally kind of like also. And what is that way? Is that, as I mentioned before, that whatever voltage step happened, it will induce the same charge across the capacitors, right? Like whatever the voltage change, the inputs in the capacitors are in series, they will experience the same charge. If they are experiencing the same charge, from that alone we can intuitively comment upon the what will be the change of voltage they'll experience, right? For example, here I have mentioned that since this capacitor is smaller, right? Since this capacitor is smaller, it will experience a larger voltage change. And since this capacitor is twice that, it will experience the half of the voltage change, right? You can easily understand from Q equals to CV, right? Since Q is same and C value is what is, and del V is the change, right? So for C, it is Q by C, and for 2C, it is half that value. It's quite easy to understand, right? So after writing this, we can just simply write a KVL, and then again we can get the same answer. Quite simple, right? And this is a much faster and more intuitive way. Now, what will happen if instead of the voltage, I apply a current, right? So here, what I have done is that first, in this example, I first tried to apply current and then I'm trying to write impulse. So let us first discuss the current case. Again, now, when we are applying a step current, when I'm applying a step current, again, it will try to put the same charge on both the capacitors, right? And again, since it will try to apply the same charge on both the capacitors, so again, the voltage drop will again be reflected by the value of the capacitors, like the smaller the capacitor, larger the drop. And again, by superposition, we have obtained, not by superposition, by KVL, we have obtained this expression. Now, VC equals to half, which is the initial condition has set, and I naught T by C and I naught T by 2C are the voltage changes respectively. Why this expression? Because I naught times T is what? It is the charge, and since it is the constant current I naught, right? That's why we have written T over here. In a very much strict sense, I must write that I must actually write I naught T along with UT so that these expressions look more complete. But for time being, we can understand that it is happening after t equals to 0 times. I'm not going into that much of a nuance. One more thing that now I must repeat over here is that one might argue that a capacitor blocks steady state current or DC current. Then how we are saying that this I naught current is flow through this network? So the idea here is that when I'm feeding a current source, it is constantly trying to inject charge into the capacitor, right? It is constantly trying to put some charge over here, and here also some minus Q charge will appear because of the pull by these Q charges accumulating here. And this is just happening and happening and happening because the current source will keep pumping the charge over here. So the idea here is that the capacitor won't reach any steady state at all to begin with, because the current source keep on pumping the charge on the capacitor plate. And so the current will flow, because as you can understand, like here is another circuit, here is another cap. So here, since Q is being pumped here, and this Q will attract minus Q over here, and because of this minus Q, plus Q charge will get created here, and again because of this minus Q will get created here. So in a way, a current will keep on flowing still, right? It will appear as the current is still flowing, because the capacitor has not reached a steady state because of this current source injecting current constantly. So that is the idea of a steady state, that a capacitor will block steady state current. But here, the current itself is not allowing any steady state condition to appear in the circuit, right? So that is the basic idea. And a capacitor blocks DC voltage. I think I said some wrong statement before. A capacitor blocks steady state DC voltage, right? So that is the basic idea. So okay, and then I have discussed. I have discussed not the same example, but some other example with an impulse. But okay, let us also go over it, that what will happen if I have this impulse, and I said that it is equivalent to I naught, and okay. So what will happen if I feed an impulse to a circuit? Again, this is an easier example. So let us go with a more complicated example so that we can understand that way. So here we have fed a impulse current. You must understand that an impulse current is what? If we integrate an impulse current, it's basically a charge. Right? It's the step function of a charge. So here again, I have in this example we have solved it by superposition, but again we could have had solved it all together by that uh, by that analogy, that that the same charge will be, that how that charge will be go distribute to the series network of capacitors. Like these two capacitors will experience the same charge across them, right? So by this we could have had basically uh, solved this question, right? So that is the main idea. Here also the same idea basically applies, that if I would have applied an impulse of current, it would have again induced the same charge over these two guys. And if you want, we can actually solve this also. The same idea basically is here, that VC, and I'm talking about this example. So this impulse is applied here, so it will be the initial condition plus integration of this current with respect to time. So it will be just a unit step function, right? It will be just a unit step function. And similarly, here also it will be just a unit step function yeah, divided by c, and here also it will be just a unit step function divided by 2c. So yeah, it's pretty straightforward. So nothing much sacrosanct or difficult about this. Now let us discuss briefly about first order systems. Here, I have given an example of a low pass system. And first of all, a very important equation to be discussing here is this. This basically comes from Laplace transform. That is that any variable in a first order system can be expressed in this fashion, where x of infinite is the steady state of value, or value at infinite time. X naught is the initial value, or the time at which the switching or any kind of a change is being put in a circuit. So we should be able to understand that this zero can easily be replaced with a T naught, where T naught is the instant at which some change will reduce in the circuit. And also in this expression, T minus T naught will appear. I think it is quite simple to understand and make such kind of manipulation in this equation. There's nothing, there's no big deal about this, right? Okay, so now this is a standard low pass transfer function. How is it low pass? We can understand that if I replace s with 0, this transfer function will be 1. And if I replace s with infinite or high frequency, this will be 0. So it's clearly a low pass system. Now, here I have written some results which are fairly easy to derive in a low pass system, that when I feed an impulse, then my output response to this transfer function will be a decaying exponential, right? It's quite simple to understand, and we can just derive it quite quickly. Even we know that the inverse Laplace transform of this and time domain is this only, right? So it's quite simple. Then ut again is quite simple, that since it's a low pass system, so it won't allow sudden change. So that means that if I'll feed a unit step, so since this unit step, this is a very high frequency change, so sudden change, so my low pass system won't be able to track this, so it will try to eventually catch up, right? So that's the basic idea, and very easily we can also put it out mathematically, right? Then it's a ramp function again. So here also it's the same idea, that if the input is like this, my output will appear in this sort, right? Again, it's again important to mention that this system at time t equals to 0 particularly behaves like an integrator, right? Now, why I'm saying at time t equals to 0, why I'm saying this, that at time t equals to 0, it's particularly behaving as an integrator, because if we observe, for example, in this ramp response only, when this time will tend to 0, then what will happen is that this expression almost is proportional to t square, right? And even here, we can see that since if we see this portion, it's almost linear, it's proportional to t, right? And we know that integration of ut is this guy only. And if we see about impulse also, so at almost t equals to 0, it is almost as if it is a unit step, although a decade later. But if you zoom this guy, it will appear, it will seem as if this guy was a unit step, right? So that's the basic idea. Great. So now uh, let us also talk about other stuff, right? Let us talk about other stuff. And what is that other stuff? Is that here we just discussed about a low pass filter, the low pass filter or low pass system. But what about a high pass system? So we already understand that a low pass system, a high pass system, we can actually understand quite intuitively. Is that if I just place a zero at the top, so why it's a high pass system now is because at zero frequency this guy will be zero, and at infinite frequencies we can just apply the L'Hopital's theorem, and we can understand that at infinite frequencies, this will be a finite function, and thus this is a high-pass system. We can understand it quite easily. And so the question arises that what will be the response to these inputs by a standard high pass system. I think we can quickly derive that also maybe towards the end, but it's quite simple really. So first of all, now we have also laid down an example in front of us. Let us first try to identify that what kind of a system is this. So it's quite easy to identify first order systems, whether they are high pass or low pass. One way is that you just check at the two extremum of frequencies at zero and at infinite. So you can understand that at zero, since this is a voltage source, by the way, so here at zero, this guy is open, and thus nothing will propagate over here. And at infinite, this guy will short, and this guy will short, and this guy is comparatively infinite as compared to a short, right? And so half the voltage will appear here of the input. So it's a high pass system. That is something we can understand. And from this also we can very intuitively and quickly sketch the transfer function. Now, what is the intuitive way to sketch a transfer function is that you identify the pole in the system and you identify the zero. Great. How do you identify a pole? We can understand that whenever there is a RC component present, there will definitely be a pole in the circuit. What is the order of the system? Since we are dealing with first order, we know that only one pole will be present in the system, right? How is this a first order system? Because we can lump all the energy elements together into one, right? Because if I remove the input over here, I can easily lump this energy element into this guy, right? That's the basic idea. Now, what is the pole? Again, how do we find pole? We find pole by basically removing the independent source in the circuit, right? So again, when we short this guy, and if we were to have in a current source, then also like it's we could have just removed it and then found the pole, right? And so basically the CC go in parallel, and this R times 2c is basically the 1 by pole or the time constant in this first order circuit. And so we can easily sketch the denominator, and we can understand that this circuit has a zero because it has parallel paths. Like we should understand the theory behind a zero, that how does zero arise? Zero arises because of parallel paths in the circuit. That's the basic idea. Because let us say that we have some parallel paths. So let us say that here we're talking about the voltage at this node, okay? And here also there is some circuitry. Some current is flowing here, some current is flowing here, some current is flowing here, some current is flowing here. So you can understand that if this sign is negative, this sign is positive, and these signs are such that they cancel the effect of each other, we can understand that because these parallel paths, a zero is possible over here. But if we have just this guy, a series, and here is the actual ground of the circuit present and some current is flowing, so we can understand that this node can't get zero. So the idea is that zero arises in the circuit because of parallel paths, and specifically when those parallel paths can have different phase, right? And here we can understand that clearly they can have different phase, so at zero will be present, right? So that is the basic idea. Now, how do you, am I bad? How do you find the zero in this circuit? You can just, any general circuit you can actually decompose as Z1, Z2, here is V out, here is your V in. So the transfer function is Z2, Z1 plus Z2, right? So when will the zero be present in the circuit? When either Z2 can be zero while Z1 is non-zero, or your Z1 tends to infinite while Z2 does not tend to infinite, right? So if you check for these two conditions, you can easily find the zero in the circuit. So here also we can understand that this RC network, this RC network, uh, what is the impedance of this RC network? It is 1 by RC, 1 plus SRC. So we can understand that this function, wait, I'll just, yes, yeah. So this function can easily become a zero at zero frequency, right? Wait, I'm doing something. First of all, I should write HPS. So we can understand that this parallel transfer function will become zero at infinite frequency, right? Why I'm saying it will become zero at infinite frequency? It will become zero at infinite frequency because intuitively also you can understand that infinity this will short, and so this parallel combination will be zero, and also by the transfer function you can understand that, right? And thus the zero will be at S, right? The zero will be at SRC, and we can understand that here the zero is present, and here we have basically fed in a step input, and this input is decaying like this, right? But a note here that there is also an impulse present over here, right? So whatever intuition we try to build, that this will happen or that will happen, this guy, this thing that we are seeing here, why first of all the impulse this direction is because this circuit had an initial condition of 1 volt, right? I think we'll elaborate more on this when we discuss high pass circuits in more detail. Let us move further, and let us keep in mind that we have to discuss high pass filter or high pass circuit in a bit more detail, so that things seem to make more sense later on, and we'll come back to this example. Now, here I have just discussed effect of adding pole zero. So, the effect of zero is basically like adding initial condition in the circuit, and LHB zero makes the circuit faster. We can actually understand it if we just try to take inverse of a system, inverse of a Laplace domain system and time domain. For example, let us take S, S plus A. Let us take 1 S plus A, right? So the inverse of this is what? The inverse of this is E minus AT UT. And what is the inverse of this guy? The inverse of S, S plus A is E minus AT UT and the derivative of that, right? Alternatively, if you don't want to find the derivative, you know that S plus A, you can just express it as what? Minus A S plus A, which basically implies that you can just write impulse, because impulse Laplace is 1, minus a e minus t minus at ut. So if you sketch this guy, it is just looking like this, right? And if you sketch this guy, it is a impulse, and then it goes like this. So what is the catch here is that when you let us say that we fed an impulse basically to this circuit, right? Because what I'm sketching is the impulse response. So basically, this response would have been this only if I would have fed an impulse to this circuit, right? So without a zero, my response looks like this, and it actually never reaches the impulse, right? But when this circuit had a zero, this circuit reached impulse, right? It tracked the input quickly, and then it decays out, right? So that's the basic idea, that initial condition helps us to reach the input faster. So that is what I wanted to illustrate by this, by sketching these impulse responses, right? So again, but that was for an LHP zero, but for a RHP zero, like for example, I have a unit step. So uh, technically, for a low pass system, the output will grow like this, right? But if I add an LHP zero, this output will grow with an initial condition. That means that it will reach its this steady state value faster. But if I have an RHP zero, we can actually solve it numerically, and encourage, if anyone has not solved it before numerically, to please do that. You'll find that the output has an initial condition, will have an initial condition in an opposite direction, and thus now the output will take more time to reach its steady state value. So this is something we must keep in mind. So the overall effect of adding a zero in the circuit is just to add an initial condition, but it won't necessarily help us. It will help us only if it's a LHP zero, and then it will help us to obtain the steady state condition, or the it will help us to track the output faster. Another thing now is that what is the effect of adding a pole? The effect of adding a pole is just analogous to adding delay in the system, right? Now we understand that a pole is basically equal to 1 by tau, and you understand that smaller the tau, faster is the circuit. So from this we can understand if tau is smaller, pole is larger, which implies that poles which are of smaller magnitude add more delay to the circuit, right? So smaller poles add more delay. So this is an intuitive picture that we can understand. This is something that we can extend to the idea of compensation also, where we know that uh, by Miller compensation, what we typically do is, like, let us say that the poles were initially like this, right? So the first pole, this was the second pole. So in Miller compensation, what we do is that we split these poles apart, right? So this pole comes here, right? This pole comes here. So what basically happens is that uh, this is a very crude graph, okay? But this pole came here, and this pole went far away, right? So what I was trying to get at is that now this pole is smaller, right? And so the bandwidth of the circuit is less, right? Bandwidth of the circuit is less, which means it is slower, right? And this is what also happens in Miller compensation, right? So that was the idea I wanted to convey. By the way, what is sketched was a Bode plot. I think we all know what that is. So that's what I wanted to convey very quickly. Here I just gone through the how to identify zero in the circuit. There's another small thing, another small or a quick way to find which cap contributes zero in the circuit. For example, in this network only, if you want to find that which cap is contributing to zero in the circuit, actually this trick helps in finding the culprit cap for zero in a much more complex network. But here also we can just use it as an example. What you do is, for example, if you're checking this cap, what you do is short this capacitor and check the output. If by shorting this capacitor at the output, you are seeing by shorting this capacitor, you are seeing that the output is non-zero, then this implies that this capacitor contributes to a zero. So when we short this capacitor, what will happen is that upon shorting, this guy is non-zero. So this implies that this capacitor will have some play in the zero. And if I short this capacitor, then I'll find that output is zero, which means that this capacitor will not contribute in the zero. So fundamentally, this capacitor is why this circuit is a zero, and mathematically I showed how we can calculate it. Now, what is the logic behind this? Is that let us say that you have an arbitrary circuit. This is not a very good example because it's too simple. Let us take the example of a basic OTA, let us say, and I'm not drawing the upper circuit just so that we can save on time. But let us say that I have a cap over here, I have some cap over here, and here I have my active mirror load, and here is my output, and here's my V naught or V output, right? So here these are three caps, right? And I want to understand that which of these will contribute to a zero. So what I'll do is I'll ground this capacitor and check the output. So my output is zero the moment I ground this capacitor, right? When the moment I short it. This implies that this capacitor won't contribute to a zero. When I ground this cap, or when I short this cap, what I find, I think I'll sketch it so that's actually easier for you to understand. Yeah. So when I short this cap, what I find is that this output is non-zero, which implies that this cap does contribute to a zero. Similarly, when I short this guy is non-zero, which implies that this guy also might be contributing to a zero. Now, what is the logic behind this? When does a cap fundamentally get short? A cap gets short at a high enough frequency relative to it. So, for example, a capacitor has some value and its impedance is this. So, at a certain high omega, this overall impedance will be low, right? And thus we can short it at that particular moment. So, in this approach, where we have some circuit and we are shorting every capacitor one by one, what we are effectively doing is that we are sweeping frequency from 0 to infinity and checking that which all capacitors are getting shorted and how is output getting affected. And we can understand that every cap contributes a pole, right? For example, there we have three caps, so we'll have pole 1, pole 2, pole 3, right? So now, when a cap got shorted, that means we are at its pole frequency, right? We are at its pole frequency. Now at pole frequency, what should happen is that since that pole is triggered and mathematically that will blow up to infinite, this guy will blow up to infinite. So if this guy is infinite and this is something, my output must be zero. That's why we're saying that if output is zero or not. Because if now the gap associated with this pole also has a zero, that means that this Z1 and this P1 will cancel each other and thus the output will be non-zero. And that's why if the output is non-zero, then that particular cap won't contribute to zero. And that is the basic idea about why this trick came about, right? And that is the idea how that trick basically came about. Quite great, right? Okay. Now here, we have just talked about realizable first order circuits using plastic components. Let's see how much stuff is ahead of us. I think, okay, so there is substantial stuff to discuss. So just so that this video does not get too long, I think we can end this discussion here for now. And in next video, we'll just quickly discuss maybe high pass systems first and just try to like get some idea into them, and then we can discuss realizable first order systems, and then we can discuss pulse response, and then we can discuss the uh, impulse and response of first order circuits. Some examples we can go through that, how we can quickly and intuitively find the response to these without actually really having the need to lift the pen. Then we can just quickly go through the RL circuits, and then we can just summarize everything all together. So if anyone was watching, thanks for watching, and maybe I'll see you in the next video. Thanks.